The name of this video is Conductor Force Isolated. In the next series of videos, in fact, we are going to consider, both for the electric field E and for the magnetic field B, the effect of forces on conductors and circuits with currents. So conductors with charges and circuits with currents. So again, back to back, we are going to consider forces first for the electric field, and so conductors, and then for the magnetic field, therefore circuits. Okay, so the first case is that of the force on conductors. It's a theoretical video. Then we will do an example about parallel plate capacitors in the isolated case. So first of all, let me just say that this idea of the force on conductors is not just something useful for electromagnetism. It's a key idea in optomechanics and quantum optomechanics. So the interaction between mechanical forces and light eventually is nothing but an electromagnetic force. What we are doing today is at the basis of all that, the entire field of research of optomechanics, or at least is the basis for that. So it's quite important, so you really need to pay attention and learn this, which is a very important physics concept. So let's consider again a system of capital N conductors. Eventually, we are going to consider all the forces in MEEE, macroscopic electrostatic equilibrium, even though, of course, in the middle of the experiment, of this Gedanken thought experiment we're about to do, there are some transients, but we wait until we reach equilibrium conditions. So we have N conductors. What is the electrostatic energy of a system of capital N conductors? You've seen this a few videos ago. So U, electrostatic, for capital N, is given by the usual famous factor of 1/2, sum, for n that goes from 1 to capital N, of Qn, the charge on the nth conductor, times its electrostatic potential Vn. The key idea of the video we are working on today is the energy conservation principle. So key idea, energy conservation P for principle. This is the key idea of all we're about to do. So, let us consider in this first video the case of an isolated system of capital N conductors. So we want the system to be isolated in two different ways. It has to be isolated first globally. What does it mean that it's isolated globally? It means that the total charge associated with this system, which is Q total, and Q total is given by the sum from small n, which goes from 1 to capital N, of Q small n, has to be equal to a constant for each n and time. Well, in this case, actually just for each time, because we are summing over all n. In this case, it's sufficient, it suffices to just say at each instant in time t. In the next condition, condition 2, locally, then we want to specify the small n. We want the Qn, the charge of each of these n conductors, is a constant at each point in time, as well as for each particle n. Okay? So globally and locally. So globally means that we enclose in the universe this set of conductors and they don't interact with other conductors outside the universe we are considering, which is our lab, typically. The local condition means that each conductor does not touch any other conductor. They don't touch each other. They are physically isolated and separated, well separated. Okay, so it's worth making a little sketch that shows what I'm talking about here. So the little sketch, we can do it up here. So this is our universe. in this box. Within this universe, we can have a first conductor, which will have a charge Q1, which has to be a constant. Then there is another conductor with charge Q2, a generic conductor with charge Qn, another conductor, let's call it, with charge Qn tilde, and finally there will be the last conductor with charge Q capital N. Each of these charges is constant, they don't touch each other, so local condition globally, there is no interaction with the external world. This is our isolated system. Now let's hypothesize that the N tilde, so also let's hypothesize that each of these conductors, so all of them except for this N tilde, they are all fixed. So for each N with N different than N tilde, they are all fixed in an inertial reference frame, of course, in this case. The center of mass and charge is fixed, whereas the nth one, we can move it. So the nth, the N tilde, can translate. By some quantity, let's call it dr vector. So this quantity will be, for example, if this is the center of mass of this object, let's say that we can translate it by a quantity dr vector. Question: what is the work due generated by the electric field forces to move Qn tilde by an amount, by a translation, by a quantity dr? Well, this work, obviously, dW, it's an infinitesimal work because it's associated with dr, has to be equal to F, the total electric force, dotted with dr, scalar product with dr. This makes sense. In addition, we know that the work of the internal forces, so these are basically, this is the work of the internal forces, this work has to be equal to minus the differential of, since we are looking only at the differential quantity of this work, so we know that the work of the external forces is the electrostatic energy, so minus the electrostatic energy is the work of the internal forces, so the dW of the internal forces, let's put internal here, has to be minus, okay, because of definition of UE, the differential of the electrostatic energy. In this case, we also put this bar, and we write down here as a subscript Q to remind ourselves that all these calculations are done assuming that the charge is constant. In the example, it will be important to remind ourselves this Q. All right, in fact, in the second theoretical part of the video, in the second video, we're going to do an open system where instead of having a constant charge, we're going to have a constant potential, voltage. So now, what is F dot dr? Of course, F dot dr, we can rewrite it as F r vector divided by small r, which is ur, times dr amplitude. This eventually is nothing but F, of course dotted here, dotted with ur, dr, so therefore this quantity is the projection along the r-axis if you want, and so we get the r component of F dr, this is the result of this dot product obviously, has to be equal to the differential minus the partial derivative with respect to r of UE at Q equal constant times dr. This is my dUE total differential theorem. dr, we can get rid of it, therefore we find the final result down here, which tells us that Fr, the force we wanted to compute on the system of conductors, is minus the partial derivative with respect to r of UE at Q maintained as a constant. This is exactly the result we were looking for. So to summarize this video, we want to investigate the forces on conductors on a system of conductors which is isolated globally and locally. Charge conservation principle is written here. That's the key of this video, so right there. This is my charge conservation principle, where I'm looking at the work of the internal forces differential because I just want to move one of these conductors by a dr, f dot dr. This is minus due, definition of ue, a q kept constant, so that's what means. And so the radial direction, the r direction of f has to be nothing but the minus partial derivative with respect to r of ue at q. In the next video, we are going to consider an open system, which is not isolated, where there is some interaction, and we will find another expression for this force, and then we will give an example where we compute this force, assuming the system isolated or open, and we will find out that we need to find the same force, okay? So that's actually quite important at the end of the day. That's it.